Hello! Here we are. I think I've got it started. This is my first live stream, so if it all goes horribly wrong, you'll have to forgive me. But it looks like I'm live on YouTube. Some of you are watching. This is nice. Hello, Accruan W Blue. It's nice to see you. Is that what I said? Accruan? Yeah. So yeah, thank you for joining me. And if you aren't joining me live, then you can also watch this afterwards. So thank you for watching and joining along with me in this nerdy journey to see Perseverance land on Mars. I'm so excited. I'm sort of nervous and excited, and mostly this live stream is just an excuse to distract myself from sitting in front of the NASA live stream and chewing my own fingers off, because that's what I always do with landings, and so I thought, why not share it with you this time? Hello everybody in the chat. Please do keep chatting with me as we go along, because otherwise I'm just going to be sitting on my own in this room talking to myself, which is nothing new, but don't normally do it publicly. So yeah, there we go. Great. So I think basically we've got about an hour and 45 minutes until the worst moment of my life now, but until Percy tries to make it down. That is, NASA are going to be streaming a live stream for the next hour and 45 minutes or so. So they'll be giving updates as well. So I will be sharing with you at points some of the interesting imagery that they will be sharing. So you don't have to have too many screens on the go. I am prepared with all manners of lights and shows of nerdy stuff, like the instruments on Perseverance and the entry, descent and landing sequence, which is the most terrifying thing in the world. And yeah, but hopefully if you're watching, you'll get a view of kind of why I love Mars and why I love Mars exploration so much, and why Perseverance is going to be so important for a field that's very close to my heart, which is astrobiology. Hopefully just by pure sheer force of will of me being nerdy at you today. So let me have a quick look at the comments. Percy, let's go! Yep, exactly. So a piece from Texas. I hope you're all right in Texas. I hear it's quite chilly and lacking in power over there. So hopefully you can see me from there. Great. So what I plan to do is just spend a little bit of time talking about some of the most exciting things about the mission. I'm going to start off talking about myself. As anybody who knows me will know only too well, I'm an only child and I love talking about myself, but hopefully it'll give you a bit of a context about why I'm doing this in the first place. I'm then going to talk about Mars and why we're interested in Mars and why we want to go there. And then we'll talk about Perseverance itself. Oh goodness, that's NASA's just come on with a vengeance. I'm going to mute that for now. Yes, so we're going to talk about Perseverance and the very exciting Ingenuity, and we'll get to that. And then hopefully that will bring us to within the half an hour of Perseverance actually landing. And then we can talk about the entry, descent and landing, the so-called 7 minutes of terror, and why there's literally nothing we can do about it. And then, fingers crossed, we'll all watch it together, and I'll probably end up in tears by the end of it. So that's something to look forward to. Great, cool. So a little bit about me. I am the sole creator behind something incredible. My name is Layla, and I was a scientist, and once upon a time I really wanted to be in the position of the people at NASA now, sending astrobiological investigation rovers to another planet, because I mean science is my passion. It's It's been a love ever since I was a little child. I didn't know when to stop asking questions, and that kind of curiosity. I love learning. So, I took as many science subjects, much to my mum's devastation, because she wished that I'd gone into art and French and English and things like that. But no, the natural world is always something that's kind of fascinated me. So I went to uni back in 2004, Oxford University, to study earth sciences, and I did 4 years there, and then I didn't know what else to do with my life, so I stayed there, and I did a PhD in paleontology and, as it turned out, paleontology and astrobiology. So my PhD subject was looking at some of the earliest forms of life and the fossils of the tiny single-celled organisms that existed a billion years ago. And although my PhD thesis was only focused on fossils that were a billion years old, some of the principles that I was proving and some of the ideas that I was looking into actually had applicability beyond Earth, and much beyond the 1 billion years that we were looking at. I was looking at ways that fossils could be mineralised inside rocks, so that we could see them on another planet or in the most ancient rocks of Earth. So that was my PhD, and again, hadn't really given a great deal of thought as to what I was going to do with the rest of my life, and so I was very fortunate to get an internship to go and work at NASA Ames in just outside San Francisco. And so it was in 2012 I spent a few months in San Francisco and working in the exobiology department in NASA Ames, doing some of the experimental work that followed on from my thesis, and which had relevance to finding fossils and finding alien life, essentially microbial life on other planets. So that's where I was in summer 2012, and the other thing that happened in summer 2012 is the last big rover landed on Mars. So Curiosity landed on Mars in June 2012, I think, and I was lucky enough to be there at the time amongst the engineers and exobiologists, just looking at these big screens in this wonderful big parade ground, and we watched as the footage came down and the telemetry came in, and Curiosity actually made it to the surface, and it was just a moment of pure scientific elation, and I really wish more people could have shared in that excitement. And I think it's so wonderful that these days we've got so many ways of sort of watching a landing like this. I mean, some of you are choosing to watch it through the medium of my stream of consciousness, of which I'm eternally grateful. But I think it's so available that people don't necessarily realise quite how much of a big thing it is. This is the culmination of literally thousands of people's life's work. And the terrible thing is that it might not go well in the end. There are so many things that could go wrong, and fingers crossed it will go wrong. No, fingers crossed it won't go wrong. Fingers crossed it will go right, just like it went right with Curiosity. How many years ago? 9 years ago now. So that's why I love Mars landings. I mean, once you've seen one, you've got to watch them all. They're the best thing out there. So here we are, 9 years on, and I'm hoping to sort of share all of this with you. I'd be interested to hear, if you want to put in the comments, what you find most exciting about Mars exploration, and what you're most looking forward to from Perseverance. But for now, I'm just going to keep on talking. So what we've got here is, I'm just checking the NASA stream, and they've got some scientists talking at the moment, so I'm going to leave it there for now. But we're going to switch to talking about Mars. Now, how do we do this? So we're going to go to this. Does that work? Yes, it does. Excellent. Mars Inception. Brilliant. Okay, so you should be able to see our lovely fourth planet from the sun, Mars. Great. So, Mars. Why do we love Mars so much? I mean, look at it. It is, hang on, do I do the right gesticulation? It is marvellous. Look at it. It's a whole planet. Fourth planet from the sun. We have heard Mars is fourth. It's nearly 80 million kilometres further away from the sun than we are. That's almost twice as far away. And so it's kind of got a bit of a bum deal because it's getting less sunlight, it's getting less heat, but it's also a smaller planet than Earth. So it's about just over half the diameter of our planet, and the gravity on the surface is about a third, which means that even though they formed at the same time, Mars and Earth have actually evolved quite differently. The smaller size of Mars means that even when it formed and it was really hot, it cooled down a lot more quickly. A small thing will cool down much more quickly than a hot thing. You can stand in the way of an angle grinder's sparks and not get seriously damaged, but if you tried to hold the large hot piece of metal in your hand, then you'd end up with burns. So that's what Mars is to Earth, not quite. But so Mars formed in the same way as Earth, lots of rocks smashing into each other, melting, turning into this great sort of molten mass of rock, and then it turned into a solid body with a hot inner core. So far so much the same, but as Mars aged, it became cooler much quicker, and that meant that the hot rock processes in its interior started to slow down a lot more quickly. So what you ended up with is a planet that is kind of freezing from the outside in. And what that means is that it doesn't have the kind of mantle convection, it doesn't have the mantle plumes anymore that we rely on Earth to keep the planet dynamic. So Earth is sort of defined almost by its plate tectonics of the shuffling of plates around the crustal surface. What was I going to say? Yeah, so the plates shuffling around the crustal surface, and at those plate boundaries, you get volcanoes, you get subduction, and you get this recycling of rock elements. And that's actually what contributes to a lot of sort of the dynamism on Earth. Volcanoes spit out carbon dioxide, and then that carbon dioxide gets locked away in seafloor sediments that then get subducted under the crust, subduction zones, and the whole thing is recycled and sort of balanced on a long-term cycle. So with Mars, that slowed down very slowly, but it did slow down, and what we've got now is a planet that looks very much like this, where there's no activity. We don't think there's actually any active tectonics or any active volcanism on the planet anymore, which is a real shame, obviously, because it just kind of sits there and looks a bit dead. But what it also means is that it doesn't have that dynamic recycling of elements and of sort of volatile things like like on Earth. So that's one thing. So Mars froze very slowly and is now kind of a frozen ball of rock. But the other thing is that Mars is that little bit further away from the sun than the Earth, which means that it is a lot colder, and so it's receiving a lot less light, a lot less heat, and so everything tends to sort of move a bit more slowly. Just to get back to the frozen ball of rock, the other consequence of that is that without a churning molten metal core like the Earth has got, Mars can't sustain a magnetic field anymore. It's got a magnetic field because there is still some, we think because there's still some movement inside, but compared to Earth, which is this big, lovely kind of swooping donut that surrounds the planet, Mars's magnetic field is all kind of misshapen and ugly, and you get bits here and bits there, and it wanders about, and and that basically means that Mars's magnetic field can't do any of the things that our magnetic field can do. Our magnetic field is very, very good at deflecting the solar wind and deflecting those sort of hyper-energetic particles that come from the sun and whoosh past us. And if they didn't whoosh past us, they would be hitting the planet and they would be damaging DNA and inside life forms. It would be irradiating us. We wouldn't last very long. But not only that, our atmosphere and our oceans wouldn't last very long either, because those highly energetic particles are smashing into the atmosphere and smashing apart molecules and essentially eroding away at the atmosphere, just like a river will erode away at the rock underneath. But the magnetic field around the Earth protects us from that. So it repels those hyperenergetic particles. So for the most part, they don't make it down to the atmosphere. In places, some of them do. They kind of get whizzed along the magnetic field lines to the poles, and that's why we get auroras. But for the most part, some of the most damaging radiation, those cosmic rays, are being bounced off into space. Now on Mars, with its misshapen, lumpy, mobile magnetic field, even if it did have an atmosphere or an ocean just like Earth's, they wouldn't have the protection that Earth's has. So that solar wind is coming at Mars and it's bombarding it and it's eroding the top layer of the atmosphere. And when that's gone, it's eroding the next layer down. And when that's gone, the atmospheric pressure isn't very high anymore, which means that there's not so much incentive for the bodies of water, the oceans, to stay where they were put. And so the atmosphere, the whole oceans goes into the atmosphere, and then the solar wind strips that off as well. And so what we end up with is a situation very much like we see now, where there's a tiny bit of atmosphere that's sort of maintained by, we're not entirely sure why, or if we are, I don't know, and no oceans, no big bodies of water, because there's not the atmospheric pressure to hold it in place and stop it sort of wafting off. And while Mars doesn't have active tectonics, and while it doesn't have its strong magnetic field, that will never change. We need to, if we were ever going to terraform Mars or sort of try and dump a load of atmosphere on there, we'd need to find a way of protecting it from the solar wind. So that's something to think about in the future. Anyway, I'm rambling. Mars, yes. So Mars, like Earth, smaller, further away, got bombarded, lost its atmosphere, lost its oceans, very sad, boo-hoo-hoo. But what that actually means is that at some point, and lots of Martian exploration that's happened up to this point, at some point in the past, maybe 1 billion, maybe 2 billion years ago, Mars probably looked quite similar to Earth. No green on the land, because even 1 billion years ago, green hadn't quite made it onto the land surfaces on Earth, but the oceans would be there. So Mars would have had oceans sitting over its lowlands, and there would have been an atmosphere and enough atmospheric pressure to maintain some of that exciting, dynamic ocean stuff. And there would have been volcanoes and, all the kind of stuff that we associate with the early Earth. And what we know happened on the early Earth, of course, is that life evolved. We don't know how. We're not entirely sure when or where. I mean, this is a real advert for early life paleontology at this point. We know nothing. No, we've got ranges. We don't know when life evolved. We don't know how life evolved, but it did. The fact that we are here is evidence that life did evolve. And so, given that we're looking at the same kind of life time range, we're thinking, well, if it happened on Earth, did it also happen on Mars? And we don't know, because we don't know how hard it is to make life on a planet. We've only just beginning to sort of paddle in the shores of the cosmic ocean, as Carl Sagan put it. We are just putting our toe in, and missions like Perseverance are some of the first that are going to be able to actually test some of our hypotheses for the first time. But we don't know how common life is in even our local solar system because we haven't been able to properly test it. It might be one of those things that just happens spontaneously wherever you get the right conditions, or it might be something that is 1 in a trillion chance. But, you know, it did happen here. Could it have happened next door? And that is what one of the things that Perseverance is going to test. It's going to see if there is a remnant of, first, a habitable environment on Mars, and second, the remnants of actual life on Mars, microbial life. So all of Perseverance's instruments are equipped for looking at things at very, very small scales and very, very small signals. But that is the stage we're at now. We know what life on Earth looked like at that point. And so we know more or less what we should be looking for on Mars to find life at the right kind of evolutionary stage. So Mars is like super cool, man. I think Mars has been one of those fascinating planets that's been in our consciousness as long as we've been, thinking and being taught about space. It was actually first seen through a microscope. Great job, yeah. Through a telescope back in the 17th century by none other than Mr. Galileo himself. I think, astronomers and planetary scientists have been fascinated with it, not only because it's so close, but because it seems like it's just that hair's breadth away from being something really successful, and yet it's failed. Famously, a scientist, Percival Lowell, studied Mars through his brand new giant telescope, and he looked at the planet, and he looked at all the strange smudgy markings on the planet, and he swore, he was absolutely convinced that he could see patches of green that moved in and out and grew and shrank with the seasons. And then he was absolutely convinced that he could see canals, these very straight-lined canals or sort of double-lined canals that went all over, crisscrossing the planet's surface. And Percival Lowell must have had quite a vivid imagination, because essentially he was the one that gave birth to the idea of Martians in all of our collective consciousness. His conviction that he'd seen these sort of growing and shrinking seasonal forests, and these so straight canals that they could only be made by a conscious hand, told him that there were Martians on Mars, that they were thriving and then they weren't thriving, and that water was becoming an issue, and they were having to build these canals so that they could get water to wherever they were going, wherever they were living. And what he saw in these, what Percival Lowell saw in these blotchy images through his brand new giant telescope, is that there is another civilization out there. There is life out there, but it's struggling. And he thought, oh, they're struggling. That means that they'll be here soon, and they're going to come and invade us. And I think he's got a lot to answer for. He's given this whole idea of alien invasion and UFOs and abductions and all of that stuff. He gave it academic credence just because he was so convinced of what he could see through his telescope. Of course we know that's not true now, because we've got better telescopes. They've mapped the surface of Mars. It doesn't change from this scale at any rate, from through the seasons. There is no water. There's certainly no green forests that are waxing and waning. But we know a heck of a lot more. And even though there are no Martians that we've found so far, there are plenty of things to keep us occupied with. So obviously there was an age of observing Mars through telescopes, and then we started to send probes out there as part of the space race. Mariner 4 was actually the first probe, and I've got a little picture of it here so we can stop looking at Mars. There we go. Mariner 4 was the first probe that actually flew past Mars, and it took some of the first the first close-up pictures of the Martian surface. And I mean, that verified more than anything that Lowell was incorrect. There was no Martian race, there was no canals, there was no green. It was a cratered wasteland, essentially. And I mean, it's very easy to dismiss it. Oh, cratered wasteland, nothing to see here, let's move on. But if you're a planetary scientist, there are so many questions just to be raised and answered by an image just as simple as this. You've got craters overlaying craters. How old's that one? When did that happen? Why is that a different shape? Why is that one faded? And so we keep sending things back to Mars. It's like we're obsessed with it. We keep sending probes and orbiters and all kinds of stuff to go and look at the planet and land on the planet. And there have already been several successful landers and rovers that have visited Mars. So this is a little stretched out map of the surface of Mars. Have a quick drink. Oh my goodness, time is flying. So yeah, we've landed loads of stuff successfully on Mars. The first were the Viking landers back in 1976. And Pathfinder and Sojourner. So Sojourner was a tiny little rover that came out of Pathfinder. That landed in 1997. And we were actually able to move around on the Martian surface for the first time. And then we've got Spirit and Opportunity. Everybody loves Spirit and Opportunity. They are the darlings of Martian exploration. And Phoenix in 2007, that was quite a short-lived mission. That was all the way up here, up in the polar regions. And then, as I said, Curiosity in 2012, when I saw it land. Curiosity's still going. And it is going to keep going for the foreseeable, I think. I haven't checked up on it recently. We landed InSight in 2018. Now, InSight's a solar-powered lander with these huge solar panels, and its main goal was to explore the subsurface of Mars. Through seismic readings and things like that. And then Mars 2020, that dot just north of middle and right of centre, is going to be our Perseverance, which is landing in an hour or so. Yeah, in about an hour. So that is super, super, super exciting. So so we keep sending things to Mars. We keep thinking of questions that we want answers, and we keep building things and sending them out. It's a great cost, but unmeasurable return for science, but also for engineering, and some of the applications that go beyond space exploration. But that's not to say that it's always been successful. Going to Mars is not easy. Don't let the success of all of those past landers convince you otherwise. There are just as many missions that have failed. Early on, there were missions that failed in launch. We still hadn't got rocket launching completely down, and rockets would sort of veer off and do strange things. There were missions that were lost in transit. They just disappeared in the space between Earth and Mars. And there were missions that made it so close, like painfully close, and then failed at the last hurdle, because landing on Mars, as we shall see later, is like, it's just unimaginably difficult. So I think it's more a testament to the ones that haven't made it. The ones that haven't made it are sort of more of a lesson and more of a reflection of how difficult this process is than the ones that did. So we had the Mars Polar Lander in 1999. That's down in the South Pole on the far right. That crashed on landing. We've got sort of Beagle 2. That was a European space agency. A British project leader was on that. That was devastating, because that would have been a big move for UK science, European science. that in 2003, again, that made it right to the last mark, and then we didn't hear anything else. And, you know, everything crossed that won't happen today. But, yeah, fingers crossed that won't happen today. I was just thinking about it, and it's the worst thing. But, you know, there are lessons to be learned, even if that does happen. You know, if it does, then I'll have to sort of wipe my face off and try and think of the positives. But there are always positives, because in just developing the science to get us to that point is just groundbreaking in itself. Anyway, getting ahead of myself. And then ExoMars in 2016, and another European venture, again didn't quite make it. So we are hoping that, building off the success of previous landers, and Perseverance is very similar to the vastly successful Curiosity in terms of both the rover and the sort of landing system. Building off those successes, we are hoping to succeed again today. So I mean, we say we, I had literally nothing to do with it other than just getting really excited about it. So yeah. So just a little slide here, just a little picture there, hopefully you can see. This is a elevation map, similar to the true colour map above previously, but this is elevation map showing where on Mars that these landers and rovers have been targeted. And what you'll see is that Mars has got quite a strange kind of dichotomy within it. It's got this lower southern hemisphere, that's whole sort of lower section on the image, is highlands, it's cratered, you've got this huge, great big crater in the bottom. It's all sort of blistered all over with craters. And then the northern hemisphere is actually pretty featureless. In here it helps that it's coloured blue because it looks like an ocean. It is a blank kind of plain landscape. You could drive for literally days and never see another rock, essentially. Obviously there is more detail on the small scale, but just looking at an elevation map of Mars like this is really cool, because you can see some of its geological history just in those features. So obviously you've got your craters, those circular holes, and then you've got these big, like 4 big pimples on the left-hand side, and that's Olympus Mons and the volcanic terrain, which geologists these days are sort of likening it to a sort of Hawaiian-style hotspot plume that formed as Mars's plate tectonics was shutting down. Instead of doing nice big sort of convection swirls inside the mantle, it would just be like, oh, I'm a hotspot, and it'll spew up this hotspot of this plume of hot material, and where it punches through, it floods out, and it keeps flooding out, and it creates these sort of very focused volcanic terrains, and that's what we've got, that sort of high red section on the left-hand side. But that doesn't really explain the sort of very low lowlands in the north. So one of the leading theories at the moment for that is that there was a collision that swiped the rock off the top of Mars. Essentially, the constraints on the collision would have to be quite small, because if it was too hard, it would sort of melt the whole of the surface, and it would sort of completely homogenise the whole of the Martian surface. But if it was a slow and kind of glancing blow, then you've got the potential to kind of just melt and sort of resurface the northern hemisphere, whilst leaving the sort of rocky lower hemisphere untouched. So yeah, that's cool. Anyway, so that was a little thing. And if you have any questions about Mars, I may not know the answer, but I'll give it a go, because I'm going to move on to talking about everybody's rover of the moment, Perseverance. This is Percy. I'm going to leave you for 1 minute while I have a little drink, and then when I come back, we are going to talk about Perseverance and how it's built, what it's supposed to do, and some of the really cool scientific instruments and some of the scientific missions on board. So 1 minute and we'll be back. Here we go. Hello, I'm back. I've had a nice refreshing glass of water. I've had a read of my comments and I'm ready to talk about Perseverance. So thank you for commenting in the live chat. If you're watching, please do. It's lovely to know you're there, and if you're enjoying it or if you're already getting sick of my voice, I want to know it all. I've never done a live stream before, and my poor husband's going to be so tired of hearing my voice after having heard it all day, and now he has to listen to it all night as well. But anyway, yeah, so let me know what you think and what you want to know, and I'll try and do my best to answer your questions. I want to say hello to Paul, who's commented. Paul was my A-level geology teacher, and oh gosh, he is probably single-handedly one of the people who have decided my course in life, because, you know, as I said at the beginning, I love all science, and it was Paul and his influential teaching that kind of led me down this path. So in a sense, you can all thank Paul for this. It's your doing, Paul. Well done. Hello to Jack Knight, age 4 in Scotland. I hope you are as excited about the Mars landing as I am. I'm sure you are, and we'll probably be doing similar amounts of bouncing at the same time, so that's good. And Artis, nice to see you. Great, okay, so let's move on to Perseverance. Right, you need to see what I can see, and that is this lovely picture. Like, I love this shot. It's such a sort of glamorous shot of Percy in action. Yeah, as I said before, Perseverance is built on a similar model, to a sort of similar layout and a similar principle to Curiosity. Now, Curiosity's name before it became Curiosity was Mars Science Lab, and I mean, I don't think anything could be truer, essentially. It was a lab, it was equipped with scientific instruments for doing all kinds of stuff. But in my opinion, Perseverance has got even more. I mean, granted, it's kind of more focused on the sort of stuff that I love, but Perseverance has got so many cameras, so many instruments, so many different geological tools. I mean, I would be delighted to have all of these tools in a normal science lab, academic science lab that is, let alone in a car-sized rover on a planet 80 million kilometres away. You know, when you just think about it like that, it's like mind-blowing. Anyway, so as it says, it's car-sized, it's about 3 metres long, 2.7 metres across, and about 2.2 metres tall. And it weighs as much as a small car, essentially. Weight is a huge issue when you're sending anything out away from Earth. Excuse me. Every kilogram that goes is going to cost more in rocket fuel. It's going to have to be slowed down. It's, you know, they are so conscious of weight, and so Perseverance ends up weighing about just over a ton, just over a metric ton, 1,000 and checks her notes, 1,025 kilos, and it is a little bit heavier than Curiosity. I think that's probably more instruments, more arms, all kinds of stuff. So so it is slightly more heavy, and that means that even though it's going to be landing in the same way that Curiosity did, it's actually going to be more mass to slow down, more inertia to get a hold of. So the risks are greater than any other Martian landing that we've ever done. So more fingers crossed, please, like literally every finger that you can possibly cross. Great. So instead of looking at this boring image, let's do something interactive. So, how do we do this? Percy. This is what we want. So this is a fantastic resource on the mars.nasa.gov site. And it is a 3-dimensional model of an infeasibly clean Perseverance rover. I can promise you that after Percy has been on Mars for about a nanosecond, it will already be dusty and mucky and all sorts of things. But, you know, in an ideal world, this is what our lovely Perseverance will look like. So hopefully you can see me manipulating them. Now, I was on Perseverance's Twitter earlier on today, and I am reliably informed that they prefer they/them pronouns, and they are Latino in origin. So please do make sure you respect that. Seriously, I think it's wonderful how the interaction of these kinds of missions with the public, the outreach, the engagement is spectacular. So more of that, please, NASA. You're doing a very good job. So here we are with Percy. So first thing you might notice is we've got some wheels, but these are no ordinary wheels. Oh no, these are. Hang on, I've jumped. Aluminium ridged wheels with curved titanium spokes for extra springiness. They're very similar to Curiosity's wheels. They are. They're surprisingly big, actually. Oh, look, we can go in. They're surprisingly big. They're actually about half a metre tall, so that's sort of knee high. So you think that this is a little toy model, but actually it's once you realise that these wheels are about knee high, you can realise that this is a serious bit of kit, and you would not want this mowing you down. So aluminium wheels, they're mounted on this kind of strange rocker bogie suspension system, and the clever thing about this is that it can drive over rocks that themselves are about knee high. So this is a lot more versatile, a lot more kind of resilient than your everyday car. It can sort of climb and mount over rocks and come back down, and it's fine. And actually, the whole of Perseverance is designed to withstand tilts of 45 degrees. So that's like she says, look at it, yeah. About 45 degrees. I mean, that is a lot, and that's in every direction. So it could be on its side 45 degrees or on its back 45 degrees. And that's great for giving it resilience on the Martian surface, but they don't want to push it. the people driving Perseverance have done a lot to get it there, so they're not going to push it. They say that they're not going to take it more than 30 degrees, which I still think is pretty steep, but so it's going to be able to drive in any direction, and it's driven from Earth for the large part, although actually the whole rover has got a lot more automation than any other rover that we've sent before. I mean, that's partly a reflection of where we are with automation in driving now. The brain inside Perseverance is one of the best brains out there, essentially. It's got this kind of advanced kind of hazard awareness system. It's going to be able to sort of see some of the things that are in its way and make a few decisions, or at least recognise them as hazards and sort of go crying back to mission control and say, I know you said go that way, but shall we maybe not? So that's really cool. I love the idea that it's actually going to be, in a sense, thinking for itself for the first time. But yeah, for the large part, Perseverance is going to be driven and directed by operators on Earth. And partly because of the delay, which can be as much as, I think, 20 minutes or something like that. The commands have to be quite simple, and actually Perseverance isn't going to go very fast. It's going to go super fast for Martian standards, but Earth standards it's like excruciating. But it's on Mars, so you can't ask too much. So top speed is a whopping 0.1 mile an hour. That's 4.2 centimeters per second. So sadly, even though it's going to land in Jezero Crater, it's probably never going to get out of Jezero Crater, even if it lives, its full mission lifetime of about 3 Earth years. It's going to kind of trace its way around the crater's edge and not get much further. So when you think back to that map of Mars, it's not going to be wandering all over the place. It's literally going to be staying in that one area. So we got your driving system, and just to talk about communication with Earth, because obviously that is critical. It's not fully automated by any means. Every command, every decision is ultimately going to be made on Earth and needs to be beamed back down to the rover. And at several million miles, that's no small task. So Perseverance is equipped with 3 different antennas. So the first one is this this black one here. So this is your ultra high frequency antenna, and this one's really cool. Hang on, let me make sure I'm talking about the right one. Yeah, so this is the one that Perseverance is going to be using most of the time, and it's not beaming data to Earth. It's actually beaming data to the orbiters that are around Mars. So you've got mind blank, can't remember. Anyway, there are several orbiters. Mars Orbiter is one. Mars Express, maybe? Not sure. So it's going to be talking to the satellites that are in orbit around Mars, and then those satellites, once they've got the data, they're going to be able to use their much bigger antennas to beam information back to Earth, back to the Deep Space Network antennas on Earth. So what that means is that we can get much higher data rates, so essentially that's going to be our main form of communication, of main way that Perseverance is going to send its information back to Earth. There is another antenna, and I think I've zoomed in now and ruined it all. This one? No, I've broken it. High gain antenna, yeah, this one's awesome as well. So the high gain antenna is another one that can talk to Earth, but this time it's talking directly to Earth. And so the high gain means it's going to have a focus beam. It can point at Earth to get the highest possible data rates, and it'll depend who it's talking to, which antenna it's talking to, as to what data rate it'll get. But the really cool thing about the high gain antenna, and you don't really see it in this model, is that the whole thing is posable. It can rotate by itself. It's like a neck. It's like when we use our neck to turn to talk to somebody over our shoulder, we don't have to move our whole body. And that has been a problem in the past. If a rover in the past has wanted to talk back to Earth, it has to sort of manoeuvre itself into a position, its whole body into a position, like this, so that it can point at Earth and then track it around. With this high gain antenna, it's got this neck. It can look around, it can look for Earth, and it can follow it through the sky. So that's a sort of really cool advancement. And you're going to have your micro servos and all kinds of cool stuff on there. And then we've got another antenna. Why do things now? I'm going to have to find it. Let's use this little thing, the low gain antenna. So this little guy over here at the back of the what's it called? Rover. Yes. Brain's already starting to leak. The low gain antenna is how the how the rover will receive information from Earth for the most part. So it's kind of omnidirectional. It can receive information from every direction, and there are low data rates. There are low data rates. But it does mean that it's there, it's always seeing the Earth, it's always receiving information. And so that is kind of our big backup, because, when we don't want Perseverance to be stranded out on the surface of Mars all by itself. So with this low gain antenna, even if the others don't work, even if the orbiters aren't in view, we know that we're going to be able to still hear from Earth and speak back to Earth from Perseverance. Cool. So, oh gosh, so much else. So while we're at the back here, let's have a quick look at this great big monstrosity. Obviously, this is incredibly important here. This is what we are calling a MMRTG, or a multi-mission radioisotope thermoelectric generator. In other words, it is a small nuclear power station. So the power source for our rover. So again, this is what we did on Curiosity. Curiosity is still working, so we know that it's pretty good model. This power source is loaded with about 5 kilos of plutonium dioxide, and unlike in sort of large-scale nuclear power stations, we're not using that plutonium to generate steam, but we are still using it to generate electricity. So as the plutonium decays radioactively, it's going to be giving off heat, and that heat is then used through exciting chemical things that are way beyond me to generate electricity. And it's going to be able to, at launch, it was creating about 110 watts of electricity. And then every year that it operates, it's going to be producing a little bit less. But the instruments on the rover and the driving system on the rover is all designed to make use of the electricity that's there. And so it's going to be able to make decisions on sort of how best to use that information. And of course, the benefit of having a nuclear reactor on board your rover, as opposed to any other sort of energy source or renewable energy source like a solar panel, which has been used in the past, is that Perseverance can go anywhere. It can go into shadow. If it finds a cliff, it can sort of nestle under there and have a look at what's under there. It can work through the night and through the day. It can work in sandstorms. It is, the ultimate reliable power source. And for any worries about, we're dumping loads of radioactive waste on another planet, I understand that the engineers have taken huge pains to make sure that, although there is 5 kilos of plutonium dioxide, it is packaged in such a way that it would never get out in one place. And in fact, had somebody been exposed to an explosion on the launch pad, they would have received less radiation from the nuclear power source than they would receive naturally on Earth in a whole year. So the risks are very, very low, and the benefits vastly outweigh them. So on the surface, nuclear power source, quite scary, but soon I reckon we'll be powering all our cars like that. No, I don't believe that at all. But it's a very practical solution for a rover on Mars. Cool. What's next? All right, let's talk about cameras. Oh my gosh, this rover has cameras. I'm just going to jump back to my presentation because I've got a cute little slide here. So these are the cameras on Mars 2020. There are 23 cameras in total. I mean, if this was going to do anything, if this rover was going to do anything, it's take pictures. That's great because we love pictures. A picture can tell 1,000 words. Pictures can be used, visual images can be used for sort of chemical diagnosis, for sort of characterization of minerals, for characterization of macrostructures, for characterization of geomorphology. They can be used to see where you're going, see where you've been, see what's up there, see what's down there. There are so many uses for cameras, and with Perseverance, they have gone all out with the cameras. Even before Percy lands, there are going to be cameras capturing the descent, and so we'll see later that there will be a moment where the descent module will put out a parachute. We've got a camera looking up at the parachute to see whether it's going or not. At that point, we've also got a camera looking down at the ground, so we can see how quickly it's coming back up to us. We've got, what else have we got? We've also got a camera on the descent stage, the jet-powered descent stage, looking at the rover to make sure it hasn't fallen off. So those cameras are going to be capturing images as they descend. Now, I'm not sure whether we're going to be getting those images as we see the descent. We'll have to keep an eye on the NASA feed for that. But yeah, certainly there will be some of the first telemetry that comes back to us, and that'll be super exciting, regardless of the outcome. So, and then once we're down, we've got, let's have a look, let's stay on here. We've got navigation cameras, those are on the turret. No, let's go back there, because we can have a little zoom in on his little face over here. So we've got the mast here with the navigation cameras. Oh no, that's the mast cam, that's one of the instruments. Nav cams, here you are. We've got has cams on the front. These are your equivalent to your reversing cameras. Those are the things that are going to be spotting the rocks that Percy's going to go, oh, I don't really think that we should go that way. All kinds of cameras. And then, of course, many of the scientific instruments have also got cameras. There is even a camera right inside the body, and we'll come to what that is for momentarily. Okay, I'm going to have to speed up because there's lots of cool stuff, and we're going to have to start thinking about landing soon. Oh my gosh. Right, so what else we got? We've got instruments. We've got the brains of the operation. That's quite cool. So the RCE, the rover compute element, there are actually 2 brains inside Percy. One is always asleep until the other one breaks, and then they can wake up. So, when you are sending a multi-billion-dollar instrument to another planet, it's very important to have backups and redundancy. And in terms of the computer element that will kind of receive the information from the sensors and from Earth and sort of choose what to do with them, yes, you definitely don't want to kind of lose out on that, because if you did, the whole thing would be gone. So we've got 2 brains, and actually, because of as I said, because of these navigational cameras and because of some of the software that's built into them, it's going to be more autonomous than ever before. And that doesn't mean sort of wandering around autonomously and choosing which rocks to drill. It's going to be making decisions about power usage and when the best time to do certain things are. So if we end up sending an instruction that says do this and then and that and this and the other, then it'll go, well, I think this needs the peak power output, so I'm going to do that first, and then this I can use my batteries for, and things like that. So it is making sort of basic intelligent decisions, which is pretty cool if you ask me. Alright, cool, we've done antennas. Okay, so one of the big things that sets Perseverance apart from Curiosity, and it isn't immediately obvious when you look at it from the outside, is... where is it? Wow. I was looking at it the other day. Oh, here it is. Sample handling. So this is an element of the structure, and it goes all inside. You can't see it on this thing, but one of Perseverance's main science goals isn't just to wander around and look at the rocks in situ, but is to actually collect samples. And this is so exciting because this is the dream of planetary scientists, to actually get a sample, choose a sample that we want from another planet, and be able to look at it in our own hands. Now, Perseverance is never coming back to Earth, sorry to say, but that doesn't mean that it can't start the process for us. So whereas Curiosity has been wandering around and zapping things and sort of looking into holes and sort of analysing things in situ, Perseverance is going to be able to find a rock that it finds really exciting, and instead of having to look at it for a day or two and then move on, it can actually collect it. It can put it in a tube inside its body, image it, and then it can wait until it finds a sort of a cache deposit place and put it down. And so at some future point, when there is either a robotic return mission or humans can make it to Mars, and that is a priority for the space agency at the moment, they will be able to find that cache of rocks, of samples, and go and study them with the full suite of scientific instruments that we have back on Earth. So that's a really cool kind of step up from Curiosity. And the internal robotics that are going on to make that happen are sort of out of this world, essentially. you've got your big arm that's going to come out and it's going to do a core and it's go, yeah, this is cool, this is definitely what I want. And then you've got, I think it brings it in, and you've got another little arm that comes out from the inside and goes, yes, I will take this, thank you very much. And it takes it inside its body, where another arm picks it up and puts it in a tube. And then a camera takes a picture of that tube, and I think we can have a look at what that camera image will look like. Here we go. Cash cam. So it'll be able to take a picture of what's inside its tube, and then it'll seal it up. And then it'll put it away, and then when it reaches a well-designated site that will be easy to find in the future, it can cache those tubes and keep them for some future period. So actually, within let's go back. So within the body of Perseverance, there are actually 43 empty tubes that are waiting to be filled with samples. So that's really cool. And there's also 5 tubes that are going to be put with the cached samples that aren't going to have any samples within them. They are going to be opened up to the Martian air. They're going to be given a chance to kind of get some ambient air and sealed up and put away. And the goal of that, they're called witness tubes, and the goal of that is to see if there's any contamination in the area. So, at every point within the construction and the launch of Perseverance and the rockets that took Perseverance, every pain was taken to avoid contamination, but who knows what can happen. There might be microbes in the atmosphere that have found their way in. So, if a future astronaut finds the cache the cache deposit that Perseverance has left there, and they open it up and they go, holy shit, there's microbes everywhere, they can look at the witness tube and see, oh crap, there's microbes here too, and we didn't collect a sample here, that's just from inside the rover. Oh god, our rover's full of microbes, it's probably from Earth. Anyway, there's lots of decisions to be made, but that's a cool way of having a control, and I think that's really, really cool. Great. Okay, so scientific instruments and oh Christ, wow, we are moving on with time, aren't we? Okay, I'm going to whiz through the scientific instruments very quickly and some of the cool things that they do, because as I said, Curiosity's first name was Mars Science Lab, and if anything, Perseverance has got even more, although as I said, it's mostly focused on the cameras, lots and lots of cameras. So the first one is called Mastcam Z. Where are you? Mastcam Z. So the goal of Mastcam Z, as you can see, it's got 2 little binocular eyes. It's a zoomable, panoramic and stereoscopic imager, which means it's going to be able to give us some kind of idea of depth of field. So it's going to be used quite a lot in surface operations, kind of working out what we're looking at and what where we need to be going. But it can also be useful, because it's zoomable, it can also be useful for having a look at the mineralogy of the surface, and that's what geologists essentially do when they go out. They've got little hand lens and lens to the eye, rock to the lens, and have a little look, and oh yes, I can see a shiny flat mineral there, that must be mica, or I can see a sort of angular pink mineral, that must be plagioclase. And we can do that without doing any kind of chemical testing, because minerals are very recognisable. So in a sense, that's one of the things that Mastcam Z will be able to do. So our next one is Supercam. Nope, we've gone to mast there. Oh god, hang on. You were there? There it is. Supercam. So obviously that camera is also set in the mast. Again, for imaging, we're hoping to get a bit more of chemical composition. So it's equipped with different spectral characters. It will be able to look at the different spectral characters of the minerals to sort of give us a sense of mineralogy at a distance. Okay, so then we've got Pixel, and I'm going to have to go to the menu to try and find where Pixel is, because it's in amongst the stuff on the turret, so you can't see very well. It's kind of folded up here, but on the front of the rover there is an arm, So you can see two sort of sections, the upper arm and the forearm, if you like, of that arm. And the arm can extend out with 5 degrees of freedom. So it's got a shoulder, a wrist, it's got shoulder, elbow, that's what that is, a wrist, so it can do all that kind of stuff. And it can, and at the very end there, it's got its turret, which has got all kinds of instruments on it. So it's got a drill for taking cores, but it's also got pixel. So this is where the fantastic NASA acronyms start. I think they've really outdone themselves with the acronyms in this one. PIXL, which is PIXL, stands for Planetary Instrument for X-ray Lithochemistry. So it's X-ray fluorescence spectrometer, and that again is going to be looking at the fine scale structure of minerals. It's sort of the fine scale elemental composition of surface minerals. And so this is going to give us the chance to do sort of more detailed analysis than we've ever done before with that kind of thing. So X-ray fluorescence. So that's PIXL. Now around here we should be able to, I've done it now. Look, I'll just go in there. Sherlock. Oh, this is good. And Sherlock comes with a little companion called Watson. So Sherlock, that's SHERLOC, stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. Now tell me that wasn't a shoehorn into an acronym, but I love it, it's great. So, and it's also got a companion, Watson, which is a magnifying glass that will help it identify where it's going to end up looking. But Sherlock is really cool because it's going to be using Raman spectroscopy, and this is the first time that it's ever been done on Mars, so that's super exciting. Raman spectroscopy, I'm not sure. Once upon a time, I knew very well what it did and how it worked, but it is incredibly useful, again, for analysing detailed elemental compositions and sort of molecular transitions. When I did my PhD, we used it to identify how much the organic matter that we found in the rocks had been cooked. So whether it was more likely to be sort of abiogenic organic matter, that's organic matter that formed without the help of life, that had been sort of through the ringer and sort of metamorphosed and squeezed, or if it was a little bit more less mature, if it was a bit fresher and kind of still had some of its structure, which would have been more of a sign that it was formed by life more recently, rather than having been formed geologically. So I don't know much about that mission, but I think that is essentially similar to what they're going to be attempting to do. Okay, so we've got Sherlock. Moving up in my favourite acronyms. Is MOXIE on here? There it is. Right, MOXIE. MOXIE's right in the middle, like that. Now MOXIE's a bit different. It's not an instrument for measuring the surface of Mars, but it's actually a technical demonstration, and there's a couple of technical demonstrations on Perseverance because we're now approaching the point where we're hoping to send humans to Mars very soon. We want to try and start to get a bit of a foothold on what we can do with the resources there. So MOXIE stands for Mars Oxygen In Situ Resource Utilisation Experiment. Again, a little bit of a shoehorn, but it's cute, so we'll forgive them. And essentially what it's going to do, is it's going to take the carbon dioxide that's in Mars's atmosphere. There's not a great deal, there's only 1% of Earth's atmospheric pressure. It's going to take that carbon dioxide and it's going to split it up, and it's going to basically release oxygen. And that oxygen, you might think, oh, we can breathe oxygen, we need that. Probably we'll take our own oxygen to start with, but yes, that is possible. But one of the big applications for oxygen made on Mars is as an oxidant for rocket fuel for a return mission. So that's been one of the big barriers to us going to Mars in the past, is actually being able to have the fuel and the oxidant. You know, that's a big mass of stuff when you think about it, to come home again. So MOXIE, if it's successful, is going to be able to split up the carbon dioxide in Mars's atmosphere, make oxygen, and potentially prove that concept for future technologies that will be able to do it on a large scale and create rocket fuel, essentially. So that is super cool. That is amazing. Okay, so more sensors. We've got MEDA, the Mars Environmental Dynamic Analyzer. Again, that's kind of in the middle. There's some prongs off the mast, and we got some stuff. That's your kind of weather station, if you like. It's going to measure all kinds of stuff that's going on around Perseverance on the surface. So you've got temperature. The temperature on Mars can vary massively, although where they're landing is kind of near the equator, so it's going to stay more or less the same, but it can actually get up to 35 degrees Celsius in the summer at the equator. So we think of Mars as cold and icy, and it can get very, very cold, but it can also get, quite comfortably warm as well. So they're going to measure the temperature. That's all useful for data, but also for helping to keep everything working. Wind speed, wind direction, atmospheric pressure, relative humidity. Literally, it's a weather station. It's a sort of weather station that we've got on our shed, but probably more operational and considerably more advanced. So that's cool, MEDA. And my absolute favourite acronym of all is, where is it? Oh, it's this a bit underneath. RIMFAX. Yes, RIMFAX, like shadow facts. RIMFAX stands for Radar Imaging for Mars's Subsurface Experiment. Now, if you can find Mars's Subsurface Experiment in any of that, I will give you a thumbs up, because I can't. But RIMFAX, there you are. So the goal of this is it's going to be a ground penetrating radar, and so essentially that's going to do radar into the ground and give us an idea of the geological structure underneath the surface without having to drill into it. So that's really cool. There's lots you can tell from a sort of geological section. You can look for layers. You can look for differences in density that could tell you that you've got different rock types. So so RIMFAX is again going to add to that suite of scientific instruments that is going to help Mars 2020 do its thing. Okay, I'm just looking at the time, because even though we are 30 minutes away, excuse me, even though we're 30 minutes away from actually seeing whether Perseverance makes it down onto the surface, right now, or at least in a couple of minutes' time, is when the manoeuvre is actually going to begin. So remember, Mars right now is, I need to double check how far it was away right now. Quite a lot of miles away. Let's say it's 80 million miles away. I need to double check, but Kimberly Bartholomew, that's an elbow. Thank you. That is an elbow. There it is. Perseverance has got one on their arm as well. There it is. That's an elbow. Okay, what was I saying? Yes, how far away Mars is. The manoeuvre is beginning, and we will talk about the manoeuvre as we go down. I'm going to jump over to Mars's journey very shortly, but Mars 2020's journey very shortly. But because there is that huge distance, the very complicated and extremely dangerous process of getting a multi-billion-dollar rover onto the surface of Mars has to be entirely automatic, because there's 11 minutes of delay. 11 minutes and 20 seconds of delay, which means that the multi-stage process can't be directed from Earth. It is all pre-programmed. All we can do is sit and watch and wonder while it happens. And so at 2027 GMT, which is 12:27 Pacific, that manoeuvre is actually going to be starting over in Mars. We won't know how successful each stage of that manoeuvre has been until until 11 minutes from now. So I'm going to use 11 minutes to talk very quickly about one more really cool technical demonstration on Perseverance that's going with Perseverance. And that is the Ingenuity helicopter. Yes, we have sent a helicopter to Mars. This is just, when I first read about this, it blew my mind. It really did. Would you believe it? Ingenuity is packaged inside this rover. Now remember that these wheels are 0.5 metre tall, so it's bigger than you think, but underneath here, in fact, I don't know, maybe that's part of it, but this is essentially an automated powered flight on the Red Planet, the first time that's ever been done. You've got this tiny little drone that is going to, it's 0.5 metre tall. Its blades are just over 1 metre wide, and it's got these cool counter-rotating blades. Unfortunately, it's not the same as the design of my favourite helicopter of all, which is a Chinook, but it sort of does the same thing. So you've got one blade going that way and the other blade going that way, which means that overall the body doesn't need to rotate. There's no sort of counter-rotation going on. Anyway. So the goal of Ingenuity is to test the principle of powered flight on the Martian surface, and I have a cute little video here that we can watch. Let me mute that. That's a bit jumpy, isn't it? I've got too much going on my computer. So I'll talk over it while it's doing it. So Ingenuity will be dropped from the belly of Perseverance at some point in the early days of the mission. Perseverance will back off to a safe distance because it really doesn't trust its own tech. And then Ingenuity will fire up its counter-rotating blades and totally autonomously will take flight, and it'll be able to make a sort of a short hop journey. I think this is a little bit optimistic, this video. It's going to get to a height of about 10 metres and fly no more than about 300 metres in a hop. And then it'll have to land and recharge its batteries through solar powered. But I mean, when you think about it, this is an incredible feat. The atmosphere of Mars is 1% of the thickness of Earth, so the atmospheric pressure on the surface. And so helicopters work by using, stop that, go back here. Helicopters work by using the air pressure as the blade slices through. They use the lift from the air. Ingenuity's got so much less air to play with, and so these blades are going to be spinning at 2,400 RPM, and they've got a real job to sort of lift this thing up. But if it can do it, if Ingenuity survives the journey and is properly deposited and actually manages to take flight, that is going to be an incredible demonstration of what we can do. It might just sound, we've put a drone on Mars, fantastic, but to actually take flight and direct flight on the Red Planet is just the coolest thing. It really is the coolest thing. Cool. Okay, so we've got about 8 minutes before we're going to start the journey, and I'll be keeping an eye on NASA's thing. So let me talk to you about, no, not ready for that one yet. What are we talking about? Journey. Yeah, so Perseverance has been en route for quite a few months now. It ended up launching on, let's see if I can find a nice picture. This one's a good one. Oh, I'll tell you what, let's talk, you can just talk to me. Oh, that's NASA. There we are. So just so you know, you're not missing out. This is what the NASA live feed is at the moment. We've got a lot of people, sadly, speaking in masks. And yeah, so this is what I am about to talk to you about. So we'll leave it with NASA just for a little moment. Perseverance has travelled 300 million kilometres to Earth. Hang on. Let's do me. There we are. Perseverance has travelled 300 million kilometres from Earth to make it to Mars, and it is within the final throes of that journey right now. But in a sense, these next kind of 20 minutes, even less, 15 minutes, are the most important part of its journey. Essentially, it's been cruising through space for months, and barring a rogue meteor or a solar flare that'll shut down all of its control electronics, it's had a pretty easy ride of it. But it's travelling at something like more than 40,000 miles an hour. It's just mind-blowingly fast. And in the next 15 minutes, it's going to have to get from 40,000 miles an hour to 0 miles an hour. And it has to do it in a way that will protect all of those fantastic scientific instruments, so that Perseverance can do its awesome habitability searching science. So yeah, it's a complicated procedure. And I remember when I was at NASA Ames in 2012, when Curiosity was landing, talking to some of the engineers there. So that was where NASA's got centres all over the US, and different bits are developed in different places. And one of the good things about NASA Ames is that it's got these huge wind tunnels, like gigantic rooms that they just rush air through. And it's where they test kind of Boeing spacecraft, but it was also where they developed and tested the parachutes that they're going to use in the descent and landing stage very shortly. And I remember talking to the engineers, and they were saying, you think we've got parachutes down, but getting a parachute to sort of slow something down like this, again, in a very thin atmosphere, and deploy perfectly without cables tangling and sort of it blowing itself out as it goes, is a feat in itself. And that's just one element, and quite a low-tech element, actually, of that sort of descent process. So when you think that, there are so many different components. So let me run you through. So NASA's currently showing us, that's me and NASA, there we are. So NASA's currently showing us mission control, a much quieter and more socially distanced scene than we're used to seeing at mission control. Everybody in their masks. Nice to see NASA branded masks, NASA 2020 branded masks. Keeping an eye on things. Let me just see if I can get... Yeah, I have got captions on here. Yeah, unfortunately. Okay, so what NASA's showing here is an animation, which I'm going to jump to a very jumpy version of. So if this aggravates your epilepsy, there we go. Please do look away for a little while, but it's quite annoying. It's because my poor computer is struggling with so many video displays and outputs in one go that I think it's just giving up the ghost. So yes, we are now entering into the stage of cruise stage separation. So Perseverance, inside its back shell, under its heat shield, has been travelling from Earth to Mars for 7 months, and it's had opportunity to correct itself on and off, just to make sure it's still actually heading for the right planet for a while. And the next thing it needs to do is essentially get itself ready to land on the planet. Now, I'm going to have a quick drink whilst you all look at that horrendous flickering. So, 10 minutes before landing, we are going to head into cruise stage separation. So the whole unit, including the rover, the lander unit, and all the protection, is spinning through space at just a casual 10,000 miles an hour. So here we are. So the first thing that's going to happen is our cruise stage is going to detach from the main lander body. And again, I should say this is a fantastic resource from NASA called EYES at eyes.nasa.gov, and you can visualise in full 3D this playthrough of the entry, descent and landing procedure. So, and if you watch it yourself, you don't have to have a look at the flickering stuff on my screen, so sorry about that. So many triangles. No, I agree. James Wilson Fenny has a question, and I'm going to address that because I'm going to forget otherwise. Is Perseverance using the newer memory metal super elastic tyres? Well, James Wilson Fenny, no, its tyres are fully aluminium with greaves to give it extra traction, with titanium spokes for springiness. And actually they've had to make them thicker because Curiosity's tyres got totally shredded driving over all the rocks. So they learnt from Curiosity, made the tyres thicker. So those are aluminium now. If anybody's got any more questions, I will be very happy to answer them as we go along. Okay, so cruise stage separation has happened, but the unit, the spacecraft was still spinning. So the next thing we need to do is to stop it spinning, because we don't want to be having to deal with a rotational frame of reference as we're approaching Mars. But we can see fewer triangles maybe over here. Okay, so it's used thrusters to basically stop that very slow spin, which was there. Oh, we're doing it live now. Oh, now that is exciting. I wasn't expecting that. Well, this is even better. So what you're witnessing now is the beginning of the real Perseverance entry, descent and landing manoeuvre. So I'm going to keep an eye on NASA at the same time so that we can switch back if we need to. I can move forward. Shall we watch it live or shall we... I'll let you appreciate this with full triangle situation. No, I tell you what, we're going to go to NASA because that is... Oh, I've made it too small now. There we go. Okay, so we're going to go to NASA and you get to hear me talk about it. Now, I wish they'd stay with it. Okay, I've changed my mind again. I do apologise. We're going to stick with the triangles. So many triangles. Okay, cruise stage separation. And I'm going to keep an eye on the time. So we've got a little while before anything too exciting happens. But the next stage is going to be the D-spin. Yeah, we've got the D-spin. We've fired the thrusters so that Perseverance is actually going to be heading straight without rotation towards the planet. There we go. And if you are thinking, oh, that's pretty big compared to Mars, what the great thing is you can zoom out and the whole thing just becomes so insignificant and so very small compared to the planet. So yeah. What do we have next? Okay, so what's just happened is 2 balance masses have been ejected. So that is basically dropping mass, like you might drop some ballast to change your attitude or to change your elevation. But the goal of that is to basically change the dynamics of the mass of the spacecraft as it's approaching the edge of the Martian atmosphere. Mars does have an atmosphere, it's much thinner than Earth's, which at this point is actually a benefit, because anything trying to re-enter Earth's atmosphere at this speed is going to really have a hard time of it. The heat that is going to be generated as all of that speed is shed through friction with the air, so the air resistance would be enough to completely burn it up. But what we have with Martian landers is that the atmosphere is so much thinner, so that we can afford to approach it at what this is showing as 10,000 miles an hour. Okay, I'm going to let you watch NASA at this point, because I think nothing much is going to happen for a while. So while we're having a look at this, yes, so we can see on the NASA feed that we're heading for atmospheric entry in about... oh look, I've made that all strange shape now. Bear with me 1 second. There. Just fix that for you. Marvellous. We're looking at atmospheric entry in 7 minutes. So we've got another 7 minutes or so to talk about some more optimistic stuff about what's going to happen when Perseverance makes it down onto the surface. So, as I mentioned, one of the main goals for the Mars 2020 mission and for the Perseverance rover is to search for ancient life on Mars. And honestly, that is never a sentence I thought I would ever be saying, because astrobiology, to people who don't know about it, is a bit of a joke. They think, oh, you're looking for little green aliens. I don't know why they're German all of a sudden. But, you know, it's very easy to dismiss. Astrobiology, oh, there's no aliens, what could you possibly be studying? Or, oh, are you studying Area 51? Can you get me into Area 51? I've heard that so many times. So, you know, astrobiology is one of these kind of optimistic pipe dreams, but it's incredible that we've got to a point now with astrobiology that we can build a rover specifically designed to go and look for signs of life on another planet. We know enough about our own geological past, about our own biological past, to know with certainty what we're looking for. And I mean, this was my dream 9 years ago when I was in NASA Ames. You know, I was trying to convince people that this was definitely something worth funding. My experiments there, yes, they were to do with fossilisation of cells on planets and the mineralogy of that, but we had to kind of dress it up as oh yes, it's also got industrial applications, and oh yes, it's also got military applications, and I'm sad to say that is probably one of the main things that drove me out of science as a main job, because science, I'm wittering on about myself, but this is important. Science for the sake of science has always been a second priority, and to see a rover like Perseverance finally sort of making the journey and unabashedly going, I am going to look for signs of alien life, is just absolutely incredible, and it's such a testament to where we are with science. And you know, you've got to applaud the scientists and the engineers and the people who applied for the grants to make it happen. You know, I think that's just incredible. So yeah, what was I going to say? Yes, so one of the main goals for Perseverance is to look for signs of alien life, but there's quite a lot of stuff that's dressed up in that. Lots of other cool science that there is to be done about understanding the past geology and habitability of Mars. So an hour ago or so I was talking about the history of Mars and how we think it was covered in water, and we think that it froze very early on and the atmosphere evaporated. We actually don't have a great deal of kind of strong evidence to prove that, just models that show how things would behave in certain situations, and the data that rovers and other instruments have remotely gathered. But this is, you know, Perseverance is going to be able to sit there on the ground and go, that's a sedimentary rock, that's a biologically mediated mineral, that right there, my friend, is a stromatolite, and that can only be built by photosynthesizing bacteria. You know, we can look at the geology in such high detail with this rover that you know, we really stand the best chance ever of understanding not only the sort of potential habitability of Mars, but also its whole evolution of the planet. And I think there's a lot to say for that from just a single instrument, albeit with 7 scientific instruments on board. Cool. And so, yeah, and the other main goal is really taking those steps towards a meaningful intention to go there with astronauts. And they've been throwing all kinds of numbers around, and I'm sure that the current state of the world is doing nothing for everybody's roadmaps and timelines, but you know, there is a goal to get people en route to Mars, whether in a NASA or a privately funded spaceship, by something like 2030, which is incredible. I mean, I'm going to find myself asking the question, do I want to go to Mars? But yeah, I don't think I will. I think I'll be too old by then, unfortunately. But apparently the European Space Agency is looking for disabled astronauts, and I have genuinely considered chopping off my leg so that I could bump myself to the top of the list, but maybe that's a little excessive. Okay, so we are 1.5 minutes away from atmospheric entry, and we're going to stick with this NASA view for a while because it's going to show us all the important stuff, and anything that's not that exciting I can talk over, as I like to do. I'm going to have a quick look at the questions. What is the parachute made of? I don't know, Tracy, I'm really sorry. I believe it's nothing incredibly technical, but we've got sort of steel wires, because your classic kind of nylon wires aren't going to be withstanding the sorts of forces. But it is a fabric. It is a fabric parachute, albeit one of these high-tech fabrics that ripstop, I think, probably comes into it very much. I'm sorry, I can't give you a better answer on that. What else have we got? Hello, Nancy. Nice to see you. And Kevin. Chris Patterson, who shares my surname and is actually my father, says, is Percy a 6x6? Indeed, Percy is a 6x6 because they have 6 wheels, and each one is manoeuvrable. Unfortunately, it's not going to be going at any great speed. As I said, 0.1 miles an hour is going to be its top speed once we get onto the surface. However, currently, if I can peer into this telemetry from NASA, Perseverance and its associated spacecraft is currently going at a whopping 5,326 meters per second, which I'm going to calculate with my calculator. Yes, I do have a calculator on my desk because no true nerd is nerdy unless they have a calculator on their desk. What did I say? 5,300 and something. Oh no. Still about 10,000 miles an hour. So yes, we are still going at a whack. So we are in a stage now known as entry interface point. So we are in the atmosphere. We're now in the Martian atmosphere. I am going to struggle to make sense very shortly because I'm excited and nervous and trying to remember everything about entry, descent and landing all in one go. But there you are. So we're in the atmosphere. Perseverance is in the atmosphere. It's experiencing heating and it is experiencing turbulence, just like a plane or any kind of a vehicle travelling through the atmosphere at any appreciable speed. It is experiencing quite a lot of heating and turbulence because there are going to be pockets of air that are warmer, that are cooler, that are denser, that are less dense, and so it's going to be rocked all over the place. It's going to hit pockets of air. And now the worrying thing at this point is that these pockets of air have the potential to throw the spacecraft off course, and the landing site is within spitting distance at this point. We've still got a lot of triangles. You can see Jezero crater now on the NASA feed, but we are within spitting distance. We are just. Does it say how far away we are? Everything is so small on this screen because there are so many things. Mac. We're going 10 times the speed of sound. We're exciting. No, I can't see. It's gone. Anyway, we are very close, and it's very important that we stay on track. So at the moment, the outer spacecraft has thrusters that can help to keep everything on track as it's still speeding at... and it is slowing down a huge amount at this point, but it is still going at more than 1,000 miles an hour. And so it's going to be jerking all over the place, and we're going to have thrusters that can correct some of those errors. You can imagine if it's going forward and it takes one big rock that way in the 30 odd miles that we've got to go from the landing site, we are going to be we're going to be way off. So it's very, very important that at this point the heading alignment, which is the stage we're in at the moment, all continues very... why is that paused? Now this is the terrifying thing, because if it all pauses and goes away, then we have the potential to lose stuff. Could you turn on the subtitles? They are, Nancy, I'm sorry, there should be subtitles there, but they're not showing up, so I'm very sorry. And unfortunately my computer, because it is a very clever Macintosh, doesn't have the ability to let you listen directly to the video. So what I'm going to do is I'm going to put this on very quietly.
Camera's reporting good telemetry log.
Right, I think I just heard the word telemetry normal, so.
We are starting the straighten up and fly right maneuver.
Oh, that is good news. Oh, I've gone. I nearly cried then. So we have just begun a manoeuvre, which I just made my yesterday when I showed my husband this. I said, what do you think SUFR stands for? And all this clapping. This is all good stuff. Yes. SUFR, the manoeuvre known as straighten up and fly right. And I can just confirm that clapping was the parachute being deployed. The parachute is out. Oh my gosh! Oh, this is all happening so much quicker than I thought it was going to. Oh, just shows when you keep talking, you've done a very good job, the internet, of distracting me. But now it's all happening at once, and I'm very terrified. So parachute's out. The next stage is heat shield separation. So the heat shield that has protected the rover as it's gone down has got to be ejected, and it's got to be ejected once it's slow enough that there's not so much frictional heating in the air. But also soon enough that it doesn't get in the way of the potential landing site. So we are onto heat shield separation, and I think that has happened. TDS navigation, yes. So what's going to happen now is that the descent stage is going to start capturing imaging. Yes, they're still clapping. Oh, it's still going. They have found their landing site. Oh my gosh. Have I got time to talk about this? No. The next stage is the back shell separation. So again, the back shell with... Oh my god. Oh, I think I'm going to... Okay, the back shell, in theory, has come off. Oh, goodness. So the back shell with the parachute should come off. Oh, now we've got subtitles. Should come off the descent stage, and then the jet, what are they called? All the words have gone. Ah! We've confirmation that the London Vision system has produced a valid solution, so they found a landing site. Oh, so has the heat shield not? The back shell hasn't come off. We got claps. Oh my goodness! Oh my goodness! So yes, jet powered descent at this point. We've got it's firing downwards thrusters to slow its descent. The rover is coming down on a crane very shortly. So it's a sky crane manoeuvre that was pioneered with Curiosity, and it is lowered on the rover itself. Is lowered from the jet-powered descent stage, and it is deposited on the surface. Now I'm going to have to turn this up.
Current speed is about 30 meters per second, altitude of about 300 meters off the surface.
300 meters off the surface. This is good. Okay. So yeah, I've sped through it.
Started our constant velocity accordion, which means we are conducting the sky crane.
Okay, so we're in the sky crane maneuver now. So the rover is being dropped from underneath the descent stage. And once the rover detects that it's touched the ground, it will sever its connection and the descent stage will fly away. 20 meters. We're getting signals from... Come on, subtitles.
Signals from MRO.
MRO. Oh, that's one of the things. Oh my goodness. I don't think I could... Your death is good. That's not a very good subtitle.
Confirmed.
Oh my goodness! Oh my goodness! Oh, little fist bumps because they're socially distancing as well. Oh goodness! Oh my god! Oh, well, I thought maybe that being on camera would stop me crying, but clearly that was not the case. Oh my goodness. Oh, oh my goodness. It will never get old, I tell you. Oh, I'm going to let you look at NASA for a little while I have a cry. Oh goodness. Oh, the cat has come to see me. Oh my goodness. Well done, NASA. Well done, everybody. I think I actually just made it worse for myself by describing how important the mission was and how dangerous the descent was. But you can't doubt these people because it's what they do for their jobs. It's what they dedicate their entire lives to. And I have got nothing but admiration for absolutely everybody in that room and every single engineer, every single scientist. And oh, right, keep talking and hopefully we'll stop crying at some point. Right, I'm going to be with you for another 10 minutes or so while I tell you all the cool stuff that's going to happen now that there's no more... oh, my BBC News alert has just told me that it's happened. Right, here we go. Here we go. Oh, let's jump in here. Right, as you can see, I've made a complete mess of my face. So perfect, great, wonderful first live stream, Layla. Well done. Thank you everybody for coming along on this ride with me. I'm just going to come up to cam full. Let's see. Let's find a nice picture of our rock star of the moment. Here we go. All right. Perseverance, Mars 2020 is on the surface of Mars in one piece, with, well, in enough pieces that the telemetry could say that it's one piece, and you know, I am happy to believe that it is in one piece. This is so exciting. This is the best piece of news that we've had for years. It's going to do so much for the entire field of astrobiology and for understanding Martian geology or areology. It's going to absolutely transform our sort of high resolution understanding of the red planet, and I'm so excited. Oh my goodness, is that a picture that's come through? Oh, hang on, you need to see this. There we are. This is the first image from, oh my goodness, Perseverance on the surface of Mars now. It comes from the engineering cameras.
This camera is mainly used.
So it's one of the HAZ cams. As I said, there were 23 cameras on board, and oh wow, that is amazing. That is amazing. It's a beautiful day on Mars. It is a beautiful day on Mars. And we've got, just to the side there, it looks like they're getting some images from one of the down-looking cameras from when they were verifying their descent.
Stand by for Steve.
Yeah. So yeah, here we are. We're on the surface, and as you can see, I didn't know when these images would start coming down. It looks like all of the antennas are working beautifully to transmit that information at some of the highest bit rates we've had so far. It is amazing to see this technology so many million kilometres away from us, working perfectly after going through the most nail-biting phase of its entire life. It will never cease to amaze me, and I was very excited. I woke the cat up. Where's he gone? Oh, he's wandered off. But yeah, it is a great time for science. Our second image is in. Our second image is in.
Okay, these we have a camera in the front and out rear of the spacecraft.
Nancy says, "You're making me cry." I'm so happy, Nancy, because we all should cry about wonderful and beautiful things like this. Oh, it is the best thing. It is the best thing. They're a little dirty, as I said. that idealised view of Perseverance in the 3D model was very unrealistic, because there is so much dust on Mars that the thing is already going to be mucky. This is really amazing. So we can see on the pictures that have come through that there are good shadows of the rover in sort of as it should be, so it hasn't been crumpled or rummaged or whatever, so that's good stuff. So it is going to take, so landing on Mars was a big step and is the most dangerous part of Perseverance's life, and from here on in it's plain scientific sailing, hopefully. And the mission specialists at NASA are planning for a mission of about 1.5 Mars years, which because Mars's years are about twice as long as ours, it's going to be about 3 years of operations on the surface. We don't want to look at him, you want to look at me and my blotchy face, don't you? So they're going to be doing about 3 Earth years worth of science on the Martian surface, which will be powered in the long term by that fantastic nuclear generator on the back of the rover. They're going to be testing out MOXIE, that creates oxygen from carbon dioxide in the atmosphere. They're going to be testing out Ingenuity, the first powered flight on another planet. And then they're going to move on to, well, I don't know what order they're doing it in, but they will also be doing these studies of the high-resolution geology around Jezero crater to look for signs of habitability and signs of ancient alien life. And, as I said, that is such a fantastic thing. That is, it's such a big thing for astrobiology and for sort of remote geology. We should all be very proud of what we've achieved, both in engineering and in optimism for science in the future. 3 years. It's going to take a few days before kind of science results start coming. Well, driving results and science results start coming in. And I can promise you that as soon as something cool comes in, I will be on my channel telling you all about it. So if you haven't already, and if you're here now, even after I've had a cry about a robot, still make sure you do subscribe to Something Incredible. And if you would like to support more crying on the internet, please do consider supporting me on Patreon. You can find the link in the description of the video. I'm going to take a quick look at the questions that are coming in. I can see the live chat's going crazy, and we'll just do that, and then in about 10 minutes or so I shall probably sign off. So if you have any questions or comments, reactions, please do share them at this point in the live chat. So Brahim Best says, respect to all the crew at NASA. Absolutely, I can't stress that enough. Not just NASA, but all of the scientific institutions around the world, because they do actually collaborate with sort of European Space Agency and various different institutions all over for the very specialist scientists. So respect to absolutely everyone. Tracy says, how many sites is Percy going to take samples from? That's something I've wondered myself, Tracy, because Percy's got 43 sample tubes inside their body, so they have a potential to take 43 samples. Their goal is at least 20, and it would make most sense from a scientific point of view to take those 20 samples from different places, so that we're maximising the kind of science that we can do on that limited number of samples that Percy can take. As to how they decide what is a good enough sample to cache, I would love to be a fly on the wall of that conversation, because I know that everybody's got different priorities, and certainly if we find a sort of micro-layered structure that looks very similar to a modern stromatolite, yes, I would say immediately put it in a pot. I'm going there right now to look at it. But other geologists or other petrologists might have other priorities, and I think there's quite a lot of discussion to say how they're going to choose which samples they take. So yes, I would be interested to hear how that decision is made in the long term. Okay, who have we got? Keith says, cheers Layla. That's very nice. No need to answer the questions. Great. Well, that's great. I won't answer any questions then. Thanks for joining me, Keith. I'm glad to be here with you, Brahim, too. James from Fenny, hello. Dupe. Yes, wonderful. Lots of love coming in from all of my live viewers. And remember that if you enjoyed this, I mean, it's only going to be 2 hours once it's uploaded on my channel, but I'll try and do some magical wizardry so that the highlighted bits are flagged, but it is going to be loaded up. And so if you enjoyed this and think that somebody else could enjoy it as well, please do share it with them. You can share it on any of the social platforms or whatever, but I love to see the really cool nerdy science behind everything in the world, and if somebody else might appreciate that too, then I would love to have them on this journey with me as well. Cool. Matt Damon's got a new rover to harvest parts from. Oh yes, he's got 2 very similar rovers, so I'm imagining a kind of chariot situation. So he's riding on Sojourner, and he's got Curiosity and Perseverance riding on ahead of him, and off into the sunset at 0.1 miles an hour. I can't think of anything better. Right, well, with that strangely bizarre imagery, because my brain is completely fried from information overload and emotional overload, I am going to love you and leave you. And again, please do share the live video when it comes out. Subscribe to Something Incredible. Support Something Incredible on Patreon if you like. Got loads of perks of behind the scenes content, artwork, and things like that. And what else do you need to do? Subscribe, share, pay me. Just carry on loving science and loving our world. Love you all, and I'll see you soon. I've got to figure out how to finish this stream. Oh, it's over there. Right. Bye bye, everybody. Have a lovely Marsy day.